Hello and welcome to our little lecture about the mole. We are going to be talking not so much about this furry little creature here, but about the counting unit. So let's just jump right into it. Our learning target for today is for 5.1. I can consistently demonstrate an accurate understanding of expressing information using given chemical quantities. For that, our topics covered for today are going to be the mole, Avogadro's number, molar mass, mole conversions, solution concentrations, though you have covered that before. I'm going to go over it again. Associated mathematical models, and I'm also going to toss in there and the associated mathematical models, how to deal with gases, even though we have covered that before. We'll do a brief review of it. And so let's jump right into it. So here we go. So we have counting units. You've seen some of these before. So a dozen being 12 things. In this case, we have those donuts. God, I want a donut now. Okay. And then we have a lot of eggs. In fact, that is a gross of eggs. I know some people think eggs are gross, but no, this is a gross of eggs. That's 144 eggs in this case, items. That's a dozen's dozen. Okay, there's 12 dozen there. That's a gross. It's another counting unit. And we can have a ream being 500, usually of paper. And of course, we can have a mole. And a mole being, you've seen this before, you will hear it 1,000 times more, 6.022 times 10 to the 23rd things. It's a little hard to say because that's what the nature of counting units is. It could be donuts or eggs or pieces of paper, or it could be, in our case, atoms and molecules and ions, and in general, particles. And so for us, the kind of quintessential thing to say about this is that 12 grams of carbon-12, that specific isotope, is 1 mole of carbon, and that's where we get that number from. Now this number comes from Avogadro, 6.022. He didn't actually discover it, but he was a famous chemist, and we will talk about what he did a little bit later. Now, you're going to have this already. I've made sure that you received it. You can print this out. You can work on it as a PDF on your computer. But either way, I want you to fill this out. I am going to summarize a whole book worth of information, several chapters of information down to this one slide. If you can get everything on it, you will be able to do it. So you want to make sure you have this with your notes on it so that you can refer back to it. And the first one we're going to talk about here is how do we go from moles to particles or things. Now, I'm also going to show you 2 different methods. The first method I'm always going to show you is the dimensional analysis method. These are usually written as fractions. Okay, so in this case, it's 6.022 times 10 to the 23rd particles per 1 mole. And the nice thing about dimensional analysis fractions is they can be written either way. So you can either have the mole on the top or the particle on the top, but that number will always stay together. So that means the 6 times 10 to the 23rd particles will always stay together, whether it's on top or the bottom, and it'll be 1 mole, whether it's on the top or the bottom, and you'll see how I switch that up. Now that's the dimensional analysis method. If you're going to use the traditional method, that's what these are. A traditional method in this case would be if you have some number of moles, you're going to multiply it by 6 times 10 to the 23rd to get to particles, and you're going to divide it by 6. You're going to take particles and you're going to divide it by 6.022 times 10 to the 23rd to get to moles. That is a lot to memorize. That is the main benefit of the dimensional analysis method, though there is one additional amazing benefit that we will get to as well. But as for right now, The last thing I want to say before we go into demonstrating some of these things is remember that a particle can be an atom, a molecule, or an ion, but we can, of course, have a mole of anything because it is a counting unit. But for us, it's usually going to be, we're going to use particles, atoms, moles, or ions. So let's go into actually giving this a try. So calculating using moles. So using Avogadro's number. And so here's our first problem. With each one of these, I'm going to go over a bunch of problems. I'm going to put up the problem. I'm going to waste a little time, and then I'm going to count down so that you can give this a try if you want to. And you can pause it and give it a try, and then I'm going to show you how I do it. For us here right now, we have how many atoms of lithium are there in 3.50 moles of lithium. So for the dimensional analysis method, which is what I'm going to focus on of how to do it, you're going to start off with your t-square and your given piece of information, so 3.50 moles of lithium, and you want to know what your target is, what you're going for, what your unknown. In our case, it's atoms of lithium, and we want to use Avogadro's number. Now, for this one, once again, I said it can be on top or the bottom. So it's 6.022 times 10 to the 23rd, in this case, atoms per mole. So where do we want to put this? We want to put it so that the moles is on the bottom and that the atoms are on the top. Benefit that way, it's the equivalent of multiplying the two. And that, you can see, we know we had to do that because we wanted the moles and moles to cross out. Okay, if we want to cross out the atoms, we would have flipped it. And we will get to that in a second. But the answer we get from multiplying these is 2.11 times 10 to the 24 atoms. Once again, I'm using atoms because lithium is a single element. So you can use particles instead. It's a nice universal thing shortcut, but I use the specific thing. And okay, what happens if we don't start from atoms, but we start from moles? Okay, let's take a look at that. For us here, how many moles of water are in 1.95 times 10 to the 24 molecules of water? As I said, if you want to try it out, pause it here, and I will give you the answer in 3, 2, 1, and here we go. We have our t-square, we have our starting piece of information, 1.95 times 10 to the 24 molecules of water. Once again, it's in molecules. We'll talk about that in a second. But that means that for Avogadro's number that we want to use right now, it would be it would be 6.022 times 10 to the 23rd molecules per mole, which means that we want to cross off the molecules. So we're going to want to put that 6.022 at the bottom. That would be right there, so those will cancel out, which means that the 1 mole ends up at the top. And of course, we have there at the end our target, which is our moles of water. And so the molecules cancel out, and we get 3.24 moles. Notice 3 sig figs. We had 3 significant figures for our first number, 4 for our second. Least number of sig figs gives us 3.24. We have already rounded it, and as I said before, if there's multiple atoms, okay, they can be the same element, they can be different elements, but if there's multiple atoms, we call it molecules, or as catch-all, you can call it also particles. Okay, now let's talk about mass a bit, specifically molar mass. So if we want to calculate the molar mass of carbon dioxide, again, if you want to practice this is a good time. I will give you the answer in 3, 2, 1. And so in order to answer this, we're going to need to know the molar masses of each carbon and oxygen. These are from your periodic table. For us here, the molar masses are in the top right. That was not going to be the same for every periodic table, so make sure you check the legend, the little listing of where everything is on each periodic table to make sure that you got the right number. But for your periodic table, it's going to be at the top right. And so in this case, we have 1 carbon, and we have 2 oxygens, so we're going to have 1 times 12 and change plus 2 times roughly 16-ish, 15.999, and these are in grams per mole. molar mass is in grams per mole. That is the unit that they are in. If you multiply out and add them up, you're going to get 44.009 grams per mole, and that means that 1 mole of carbon dioxide, that means 6.022 times 10 to the 23rd molecules of carbon dioxide, have a mass. Okay, if you had them on a scale, they would weigh 44.009 grams. Okay, so let's go back to the table. Where does that fit in? Well, that would be right here in our mass section if we want to go from mass to moles. And I label it as hashtag, sorry, no, not hashtag, pound sign, or the number of, in this case, that's what we care about, the number of grams per mole. So whatever we got from the periodic table, or we calculated from the periodic table, is the number of grams per mole is going to be our fraction. And once again, that could be on the top or the bottom. The moles can be on the top, or the grams can be on the top. But the number always goes with the grams in this case. And if you're using the traditional method, we do want to add those as well. So if you're going from moles to mass, you're going to multiply by the molar mass, and if you're going from mass to moles, you divide. But of course, if you're using dimensional analysis, you don't have to memorize that. It is easy enough to see once you try it. So let's go ahead and do that. Let's try it. Okay, here we go. Molar mass as going from moles to grams. Here's our first problem, and that is going to be how many grams of lithium are there in 3.50 moles of lithium. This is pretty straightforward problem. All the problems we've done so far are all like very simple, and I'm going to try and keep that way, but I will show a few more complicated later on. So if you have ready for the answer, here we go. We are going to start off with our known piece of information, 3.50 moles of lithium. Our target is going to be grams. We're going to need to know the molar mass of lithium. And once again from your periodic table, and where that is 6.9412. That 2 means digit of uncertainty because of parentheses. Don't worry about that too much. It's fine. You can include it or not, depending on how many significant figures you need, but I'm going to include all of the numbers given from my periodic table. Just know that if you use a different periodic table, you might have slightly different numbers, especially at the end. So you might get different things. So I'd recommend keep it to the periodic table we gave you. That way our numbers come out exactly the same and you don't have to worry about did something questionable go on. We will try our best to catch it though. Here's the answer though. So now that 6.941 is grams per mole, which means we want the moles on the bottom to cancel out, which means we're going to put that there and the grams will end up on top. Here is the whole thing, and then that gives us moles and moles to cancel out, and an answer of 24.3 grams of lithium. Very straightforward. What about the other way around, however? Let's get to that. So, calculating the molar mass using conversion from grams to moles. So here's our question. How many moles of lithium are there in 18.2 grams of lithium? And we're going to go to the answer in 3, 2, 1. Here we go. And we're going to start our known piece of information, 8.2 grams of lithium. And we're this time, once again, this time our target is moles. And once again, we're going to need the molar mass of lithium. And so for this, once again, and this 6.9412 is grams per mole, but we want grams on the bottom, so that means that 6.9412 is going to end up on the bottom so that the grams and grams cancel out, which means moles on the top. And now we can cancel these and give us an answer of 2.62 moles of lithium. So far, so good. Let's make this a little bit more complicated. These have all been one step. What if we have multiple steps? Okay, so calculate multi-step problems with, in this case, Avogadro's number and molar mass. And for your question for this one is going to be how many atoms of lithium are in 18.2 grams of lithium. If you want to try it yourself, stop here. I will give you the answer in 3, 2, 1. And here is what we're going to do. We're going to go from mass to moles, and then from moles to particles. Hence the whole setup of the flower. We can end up going from in the middle, anytime we want to go from one of those outside ones, back to moles. Okay, so how do we solve this? Well, we're going to start off, as I said, we're going to start from mass, because that's our given piece of information. So our mass for this was 18.2 grams of lithium. Again, we're going to need, in order to go from grams to moles, because moles is our central target, that's how we get to in the middle, we're going to need the molar weight. Oh, there's our target, and our molar weight, 6.9412. And this time, do we want that on the top or the bottom? What do you think, the 6.94? Do we want that on top or the bottom? That's right, we're going to want that at the bottom, so grams and grams cancel out, and that will give us, now we have moles. You notice that's the only unit left. This is the glorious thing about dimensional analysis, is you can do progressively, and each step tells you roughly what you need to do next, because you know you have to get rid of a unit you don't want. I don't want moles, I do want atoms. How do I go from moles to atoms? And how do I get from moles to atoms? That's right, Avogadro's number. And for that, that's 6.022 times 10 to the 23rd. Is that going to be on the top or the bottom? Is that 6 on the top or is on the bottom? Is the moles on the top or is the mole on the bottom? We want the moles to cancel out, so the moles has to be on the bottom, and the atoms in this case, remember because it's lithium, you can't say particles or you can say atoms because it's only one thing. It's on the top and the moles on the bottom, which means we can now cancel these out. Notice that the only unit left is atoms, so we can do this in one. I'm showing you the easy method. There is a faster way, but this is the easy one, least amount of thought, and that is you take all the top things, you multiply it, and then you divide that by all the bottom things, and so in this case we would get that, and an answer of 1.58 times 10 to the 24 atoms of lithium. What's next? Oh, next is what Avogadro really did. He worked with gases. This is the famous thing he came up with, is equal volumes of gases at the same temperature and pressure contain the same number of molecules. That is what Avogadro came up with. What does that mean? Well, if there you have something called STP, a standard temperature and pressure. At STP, aka 0 degrees Celsius, at 0 degrees Celsius being 273 Kelvin, and 1 atmosphere. So that's basically, it's kind of cold plus, atmospheric pressure. So what you're at basically now at sea level. Okay, but what that means is that we can now get the molar volume from that if we calculate it. So what that means, if we take PV equals nRT, our standard ideal gas law equation, and we're going to input our standard temperature and pressure for 1 mole. Okay, well, 1 atmosphere at 1 mole times the ideal gas constant, that is 0.08206. Yes, you do want to memorize that. Atmospheres, liters per mole Kelvin. And you do want to memorize the units as well. They are going to come back, and the ideal gas constant, R, is going to be dependent on those units. You can imagine if I change any one of them, the number will change. And then, of course, our 273 Kelvin. This has to be done in Kelvin when you do these calculations. Make sure you do so. Again, P for pressure, V for volume, N for moles, R for gas constant, and T for temperature. If we do a little calculation quickly, what do we get? We get that the volume is 22.4 liters. What does that mean? Well, it means that for 1 mole of gas occupies 22.4 liters of volume at standard temperature and pressure. That's very useful because it's a nice little shortcut, and so that's for us here back at our flower. That shortcut is at STP right there in the middle. Once again, here is the dimensional analysis version. It is the fraction. It is the And so you have 22.4 liters on the top, 1 mole on the bottom, and as always, it can switch as you need it, so you can have it the other way around, whatever you need to cancel out your unit. And if you do want to work with the traditional method, you would, what you would do if you want to go from moles to liters is you would multiply by 22.4, and if you wanted to go from liters to moles is you would divide by 22.4. Okay, let's take a look here. Well, calculating using the moles of gas using the standard molar volume. Well, here's our first question. I will give you a few seconds to try to pause, try it out if you want, but how many moles of hydrogen are in 100 liters of hydrogen? I will start in 3, 2, 1. Well, here's our starting amount. It is 100 liters of hydrogen. Our goal is moles, just as before, and our conversion factor is 22.4 liters as per mole, which means we want the liters where? Top of the bottom? The 22, should that be on the top of the bottom? That's right, it should be on the bottom, which means 1 mole is on the top. See, I switch it up on you, the order, but here we go. The liters and liters cancel out, and that's why we did that. That is the equivalent of dividing by 22.4 if you're doing the traditional method, and that gives us 4.64 moles of hydrogen gas, H2. Okay, what about the other way around? Okay, it's this same kind of idea, and here we go. How many liters are occupied by 3 moles of oxygen gas at standard temperature and pressure? And I will start in 3, 2, 1. So we start off with our known piece of information, 3 moles of O2, and our goal in liters, and we're going to go for 1 mole this time, and the 22.4 liters on the top. Why this way? That's right, we want to cancel out those moles. So in this case, it's the equivalent of multiplying. So you're going from moles to liters, we're going to multiply, and that's 67.2. Now I made a mistake here. Can you spot what mistake I made? I'll give you a second. So, maybe 1 or 2 of you got it. Hopefully you all did. Is I have too many sig figs. Look at that. I have 3 sig figs in my answer. 67.2. But my given piece of information, 3 moles, has only 1 significant figure. I should have written it as 70 once you round it, or in scientific notation as 7 point times 10 to the 1. But that will do for now. Nobody's perfect, and hopefully you'll learn from my mistake. Let's move on. Let's do a multi-step problem this time using these. Okay, well, how many liters are occupied by 1.204 times 10 to the 24 atoms of argon gas at standard temperature and pressure? I'm going to start this in 3, 2, 1. Here's the plan. We're going to start off from particles to go to moles, and from moles, we're going to go to liters. And so here is our setup. And what's our starting piece of information? That's right, it's 1.204 times 10 to the 24 atoms, or particles if you prefer. And what's our target? Liters. Okay, so now, how do we get, we need to go from particles to moles. What are we going to use to do that? Avogadro's number, 6.022 atoms per mole. We want the 6 on the top or the bottom? On the bottom. So they cancel out, 6.022 on the bottom, moles on the top, and atoms and atoms cancel out. Once again, we only have moles left as a unit. That's the only thing we have to deal with. Okay, and how do we get from moles to liters? Oh, we have the standard, the molar volume, which is 22.4 moles per liter. So that means we need the moles on the bottom, liters on the top. And so that's going to be 22.4 moles per liter. Moles cancel out, leaving us only with liters. And this calculation. Once again, this is the easy way. Take all the things on the top, divide by all the things on the bottom. Just make sure you have enough parentheses when you put it into a calculator, especially if you have multiple things on the bottom, because that can mess with you. And our answer for that is 4.279. That is liters of argon. Okay, next. Okay, we have done seemingly everything except for the red. But no, there is something left. That's the gold. What happens if it's not at standard temperature and pressure? Guess what? Most things aren't. Well, in that case, we're going to have to use PV equals nRT again at any temperature that is not the standard temperature and pressure. PV equals nRT. And so a problem like that might be something like this. So this is non-standard temperature and pressure. How many liters are occupied by 1.24 times 10 to the 24 atoms of argon gas at 1.2 atmospheres and 100 degrees C? This is a pretty standard question. And if you are ready for the answer, let's get to it. Okay, so we have our t-square, our given piece of information, which is the number of atoms, and our goal, which is moles. Because guess what? PV equals nRT needs moles. We have pressure, we have temperature, we have volume, we have moles, and that's it to enter. Well, then we're given the pressure, we're given the temperature, we're looking for the volume. That only leaves us with moles, and that's how we get from atoms to moles. And how do we do that? Avogadro's number, that's right. And the 6.022 top or bottom, it's going to be on the bottom. And that's atoms of argon. And at the top is 1 mole of argon, which gives atoms to cross off, and an answer of 1.9999 moles of argon, which we can now put into PV equals nRT. Well, we know the pressure. We're looking for the volume, so I'm just going to leave that as V. We just calculated the number of moles, so that's N, remember, so that becomes our green one. And the gas constant as before, 0.08206 atmospheres liters per mole Kelvin. But I didn't put in temperature. Why? Because temperature has to be in Kelvin. Well, ours is in Celsius, which means we have to convert it first. So 100 Celsius plus 273 equals 373. We'll put that in. A little bit of plug and chug, and we're going to get out from that is 49.7 liters of argon. Okay, what about the other way around? It's a little bit more difficult. So this is how many grams, let's say, of helium gas are there in a 2.5 liter balloon of 270 Kelvin. Notice there's no degree for Kelvin. That's because it's an absolute unit. It's not by degree. Interesting little factoid. You're not going to get penalized if you put a degree of a mistake, but just so you know, Fahrenheit, Celsius gets degree, Kelvin does not. With a pressure of 3.0 atmospheres. Okay, I should have given you enough time to pause it if you wanted to. So let's get into it, which is this time we're going to start from PV equals nRT because we need the moles to get to the grams. So we're going to start from P equals nRT. So our pressure and our volume and our temperature are given. So let's input all of those things along with the gas constant. And this time N, our moles, stays by itself. Plug and chug, and we're going to get 2.95 moles of helium. Notice my little tiny 5. Oh, isn't it cute? Why did I put a little tiny 5 there? Well, the thing is that I only get 2 sig figs for this, right? So I get the 3.0 is 2 sig figs, the 2.5 is 2 sig figs. So my final answer should be in 2 sig figs. However, if I round it before the problem is early, I risk a rounding error. So I keep 1 extra digit, and I put it small so I know that it's not one of the ones that's significant. It's not a sig fig, it's a not sig fig. So I just keep it there so that I don't round early and lose some numbers. If your answer is off by like the very last number, that is probably why you probably rounded differently than the person doing the exam. Okay, so let's get to how do we get from there? Well, we're looking for grams. We have our moles of helium, so we need to know the molar mass of helium. Where do we get that from? Yeah, the periodic table. And so for us, helium here, 4.026 grams per mole. That means that the 4 is going to be on the top or the bottom? The top, and the moles on the bottom. That's because moles and moles want to cancel out and give us 11.807 grams of helium. But what did we say? We said, well, we started with 2 sig figs. We should finish with 2 sig figs, which means that now I can round to 2 sig figs, and I get 12-ish. That's the rounded, the little two wavy equal signs, and it's about 12 grams of helium. Okay, almost done here. We're in the home stretches. How do you get for a solution? Now, once again, you've done this one before as well, so hopefully it is not too unfamiliar. And so it's going to be molarity, and that is number of moles per liter. Okay, and if you're doing traditional method, that is, if you're going from moles to liters, you're going to divide by molarity, and if you're going from liters to moles, you're going to multiply by molarity. Now, a lot to remember, which one you multiply, which one you divide, hence I recommend the dimensional analysis, but I will leave it up to you which one you prefer. Okay, let's jump into this one. Okay, calculating the mole solution using molarity to convert volume to moles. Here's our question. How many moles of HCl are present at 2.20 liters of a 6.6 m aqueous solution? If you want to solve it, pause it now. If not, here we go in 3, 2, 1. And here is our t-square. And we have 2.20 liters of solution. That's our given piece of information, our known. And our unknown, what we're looking for is moles of hydrochloric acid, HCl being hydrochloric acid. And we're going to use the molarity being in moles per liter. So that's 6.66 moles for every 1 liter, which means that, do I put that on the top or the bottom? The 6's. That's right, the 6 is going on the bottom. Nope, the 6 is going on the top. Sorry, my mistake. I was saying that backwards. I wrote it correctly on the screen. The liters will need to go on the bottom. It is 6.66 moles on the top of HCl for every 1 liter of solution. Ooh. So that is the equivalent of multiplying the two. Okay, and what do we get from crossing out the liters? We get the moles, which is what we're looking for, and that comes out to be 14.7 moles. Okay, what about the other way around? What if we're going from moles to liters, to volume? And so we have this question: how many liters of 3.2 molarity table salt NaCl solution are needed to contain 5 moles of NaCl? Okay, so this is the stuff you put on your food. It's table salt. Okay, here's our solution, and you start off with our t-square. Okay, pause it if you want to try it out first, but here we go. 5 moles of NaCl, that's our given piece of information. Our unknown is going to be liters of solution. You notice how many liters of this solution is the actual question. Make sure you get the units right. The moles are just of sodium chloride. The liters are going to be of solution, because molarity is going to be moles of solute for liters of solution, which means I need the moles now on the bottom, which means that 3.2 is going to be on the bottom, so those can cross out, which means our liters of solution are on the top. SOL period being an abbreviation for solution. Moles and moles cancel out, giving us a 1.5 liters of sodium chloride. Okay, now let's try a hard problem. This is where dimensional analysis really comes into its own. If you try no other problem on your own, this is the one that you want to try, and you want to try it a few times you can. And that is, how many milliliters of 8.250 molarity KCl solution could be made out of 0.631 kilograms of potassium chloride? Okay, so if you want to try it, pause it now. If not, we're going to get started in 3, 2, 1. And here is our map with our plan. I'm going to start off from kilograms because that's a given piece of information. From kilograms, I'm going to go to mass, okay, using the metric conversion from kilograms to grams. Then I want to go to our central a guy in the path, that's moles. That's always when we're trying to get from one to another, that where we have to go to first. And then from moles, we want to go, in this case, it wants milliliters of solution, so we have to go bottom left. That gets us to liters of solution, which means that we have to do another metric conversion to get to milliliters. So that's a long set of steps. But in order to get this, we already said we need the molar mass. That's the green path, that's with the arrow to get from grams to moles. So how do we get that? We're going to need to know, our components are potassium and chlorine. Those are the molar masses as given from the periodic table. Pretty easy to calculate. There's only one of each, which means you just add them up. If there was multiple, of course, you'd multiply the appropriate amount. But in this case, very simple. You get 74.551 grams per mole for the molar mass of potassium chloride. Okay, let's start the actual solution. Big long t-square here, known piece of information, 0.631 kilograms of potassium. Our goal way down there at the end, milliliters of potassium chloride solution. So we are going to go and we're going to do the metric conversion. Okay, so that, remember that the kilograms has to be on the bottom so they cancel out, and a gram is 1,000 or 10 to the 3 kilograms. So the 1,000 grams equals 1 kilogram. So we can use this in dimensional analysis as a fraction, one above the other. And so kilograms and kilograms will cancel out, which means that now we have grams, and we want to get on our second step from grams to moles. How do we do that? Yep, the molar mass, which is figured out, and we're going to put the grams on the bottom so that they cancel out, and there we go. Leaves us with moles. Notice how each step shows you just what the next one has to be, because you've gotten rid of every other unit. To progress, it's what unit do I have will get me to the next one. And so in case of moles, we're going from moles to liters. What converts from moles to liters? Well, that's the molarity, right? And molarity in this case is 8.5 moles per liter. And so we want the 8.5 on top and the bottom. Yep, on the bottom. So there we go, 8.5 moles of potassium chloride on the bottom, and 1 liter of potassium chloride solution on the top. And now that we can cancel out the moles, we are left with liters, but they do want it in milliliters. So we're going to do one more conversion, and 1 liter on the bottom is equal to 1,000 milliliters on the top. Liters and liters will cancel out if we do it this way. This will give us our final milliliters. Now we just have to punch this into a calculator. And this is the traditional way of doing it. This is the that gives us 996. That is the easy method. It's everything on the top divided by everything on the bottom. Notice that I added an extra parentheses around the bottom and the top to make sure that they are counted as a whole. Because if you have especially multiple things at the bottom, if you don't put a whole parentheses on it, it won't understand it. Now, there is a fast way, and that's this one. It is more complicated to understand, and therefore more likely that you might screw something up, because it does have some nitpicky rules on how you do it, but you can see it's significantly less parentheses to write and much faster. If you want to know more about that, talk to me during office hours or during Mondays, or if we have some extra time during class. Other than that, you're done for now. You can go ahead and start your next assignment. Have a good night.